It is my distinct pleasure to introduce George Karypis, who is giving our faculty seminar this year. George is one of those guys that's sort of legendary, both as a grad student and as a professor, because I think in an average year he gets more citations than I've had my whole life. He's done amazing work in data mining and big data. The work on parallelizing graph algorithms. So there's a handful of tools that he's written that are used all over the world. A tool called Metis, ParMetis, which is a distributed and parallel version of Metis, and HMetis. So Metis deals with graphs and HMetis deals with hypergraphs. And these have been found their way into all kinds of disciplines, because it turns out that a lot of people have graph problems. And they've gone as far as bioinformatics and different branches of engineering. So his work has been widely distributed across not only computer science, but many subdisciplines of engineering and medicine. And if you want to talk about big data, he's the guy. So even if he wasn't a faculty member here, he'd still be one of the guys I'd be trying to get to come. And he's not getting paid for this, so this is part of his payment.
I'm interested.
But he has over 50,000 citations for his work. He's a full professor and assistant department head here in the computer science department. He's also made contributions in high performance computing, information retrieval. So he's done an awful lot of good work, and I'm very excited that he can give the talk on big data. And as soon as I finish grading the midterms for year 2, I'm going to try and come down and catch the rest of the talk. So let's welcome George.
Thank you. Good afternoon, everybody. So I teach the data mining course this semester in exactly the same classroom. It meets at 9:30. So I'm used to say good morning, everybody. So I had to actually, pause and say good afternoon to everybody. So Mike asked me to talk about, what did he ask me to talk about? He asked me to talk about machine learning. I said, I'm not a machine learning guy. I do data mining. I said, that's fine, same thing. I said, well, not quite. But and then I asked him yesterday, how long is that presentation? He said 3 hours. So, only 3 hours? So, and he said, you can finish early. I said, yeah, but how about finishing late? So, anyway, I pulled together some slides, and those slides are primarily from the data mining course that we teach over here. It's a very kind of a high-level, condensed version of some of the material, and the whole purpose of the next 4 hours or so. I think I have something going on at 4, so definitely we'll finish by then. Is to give you guys an idea about data mining and what is data mining, expose you guys to some of the problems that people in the data mining community are trying to solve, and machine learning is part of it, right? Give you an idea about some of the algorithms that we have developed. Most of the algorithms will be very high level. A couple of them will go a little bit deep, so you guys can appreciate the computer science, behind that. My personal background, I want to consider myself to be an algorithm person, so I get really excited about deep stuff, right? So, and if you see me going very deep on a particular topic, you can yell and I'll stop, right? So, so what's the norm over here? You guys take a break or you don't? You do.
A couple would like to.
You like to. Okay.
It's up to you.
It's up to me. Okay. So how many of you guys know something about data mining other than data mining? Okay, so pretty much I can say anything I want to say, right? So that's good. So I mean, data mining started about 20 years ago or so, which is, for computer science, it's actually a long time, right? For a different discipline, it may not necessarily be a long time, but and the whole thing was kind of motivated by the fact that there were a lot of data becoming available even 20 years ago, right? And that thing, of course, hasn't changed today. And the amount of data that exists, comes from different domains and different applications. And there was a belief back then, and it's still today, that that there is a lot of value, right, from analyzing the data, right? So, and companies, have adopted the philosophy of, let's collect as much data as we can, right, and then try to do something, useful with the data. Okay, so so again, so data mining, comes in, the kind of, I usually want to think of the need from data mining or the desire to mine data or to analyze data coming from two different domains. One is the commercial viewpoint, right? And the other one is, the scientific viewpoint, right? So the commercial viewpoint is we have, companies like, Google, Facebook, Amazon, Yahoo, and all those guys, right? They generate and collect an enormous amount of data. I was updating my slides, this year, and the earlier version of my slide has Facebook had about 1 billion active users. I guess somewhere between there were another 1 billion was added, right? So this is an actual accurate number, right? So Amazon has like 1.1 billion orders a year. I think mine is about 100 of them there, right? I don't know how many you guys have, right? So I mean, this is a huge amount of data, gets collected and generated from a lot of companies out there, and there is value in analyzing the data, towards number one, serving you, more personalized ads, trying to figure out, what are the stuff that you like, so that they can stock more of that stuff. They can design new products for you and new services, and so on, right? And there's a huge competitive pressure, right, for people to actually extract as much value as they can, from the data they collect. Okay, so the commercial viewpoint really from data mining is data equals money, right? At some point in time with some analysis in the middle. Okay, so on the scientific viewpoint, right? So we have a lot of systems have been developed and have been deployed, right, that they are collecting enormous amount of data, right? So we have, satellites, we have, a lot of biological and life science experiments. For those guys who haven't seen a picture like that, this is like a spotted microarray. We have, Earth monitoring climate type of data, right? So nowadays we have, a lot of IoT infrastructure, sensing and collecting data in a continuous basis, right? And the idea there is by analyzing the data that we're collecting, we can actually gain insights about, the different sciences in which, the data is being collected, right? So if you guys remember, I'm sure at some point in time have seen a diagram that said, the pillars of science, and I don't have the diagram. It's consisted of theory, right? Observations and experiments. You guys remember that? Seen something like that, right? I would say 20 years ago, people put another fourth pillar that has to do with computation, right? So then essentially computational-driven science, right? And nowadays we have a fifth pillar, which is data. Okay, so this is really how science is done, right? So we develop theories, right? We observe phenomena, right, and trying to make sense out of them. We're trying to learn from experiments, right? We try to learn by running simulations. That's the computational part, right? And then the other part is, you're trying to learn by analyzing, large amount of data that we're collecting to try to gain insights about the underlying, scientific principles, guiding, the thing that we're studying. Okay, so this is the new paradigm, or at least the introduction of a new paradigm of how science is being done. Okay, so to satisfy kind of those needs, the field of data mining kind of was created, or I would say a lot of the activities coalesced into what ended up being called data mining, right? And data mining has people tried to define it a few times. And I think I have put over there two different definitions of it, which pretty much say the same thing, right? So the first definition says a non-trivial extraction of implicit, previously unknown, and potentially useful information from data. This is a very conditional statement, right? And then the other one is exploration, analysis by automatic or semi-automatic means of large quantities of data in order to discover meaningful patterns, So if you Google, definition of data mining, you're going to hit something like that. Okay. So, but there are some key components in both of those definitions, right? So, so there's a notion of an exploration analysis that is, non-trivial, in other words, non-obvious, right? There's a component of data that you analyze, right? And there's also the component that you discover something that was previously unknown, right? So essentially, that's the whole idea of mining, right? So you're mining for information and knowledge that you did not really know. Okay? And and people came up with some sort of a kind of a block diagram in terms of how the data mining process, or what is called the knowledge discovery from databases process, it's called the KDD process, right? And I was told to look at here, right? So so we have input data. There's a bunch of operations that we do over here to do the data pre-processing. Things like extracting, selecting features, reducing dimensionality, normalization, picking up the right subset. Then we apply a bunch of algorithms, so that's where the data mining stuff comes in, and this is really what I'll be talking about, right? And then you do some sort of a post-processing to try to make sense out of the stuff that comes out, right? And quite often that thing is an iterative process. Once you apply your algorithm, you see some of the stuff there. There's something weird in my data. Maybe I should go back and, clean them up better, okay? And go through the whole process, right? And then, the information comes out on that side. So within that process, the KDD process, right, most of the people in academia spend their time here, right? Most of the people in the industry spend their time here and here, okay? Getting the data into that process, right, is, people have, I've seen estimates saying something like takes 90 to 95% of the effort, right, in actually getting the data ready to be analyzed, okay? And and I gave my students an assignment a couple of days ago in which I truly had them go from here, go crawl the web, grab some data to do something, and they're panicking because they're realizing we'll spend most of the time, crawling the web, getting the data, cleaning them up, extracting all the stuff that they need to extract in order to spend 5 minutes analyzing them, right? So that's going to happen, okay? So anyway, so this is really the the KDD process, or that it's widely used nowadays, right? To in many companies, as well as to aid in scientific discovery. Okay, so what is exactly data mining, right? So if I'm a statistician, I will say there's nothing new. Okay, and up to a point, this is true. Okay, so I mean there are very few new, I will say, high-level concepts that were introduced by the data miners in the field, right? But the fundamental challenge they have been trying to solve, and they're still trying to solve, right, is really how to deal with the size, variety, essentially all the V's, velocity, veracity of the data, okay? And I have my V slides, right? But if you look at the methods that data miners use, right, they come in from AI, machine learning, pattern recognition, statistics, databases, right? So those are I would say, some of the core methods, right? What they have done, meaning what we're doing, is taking some of those ideas and actually make them robust, right? Make them to work on extremely large data sets, okay? Being able to handle the heterogeneity that exists in real-world data, okay? And actually really kind of make them, I would say, ready to be used in a real scenario, okay? So, and a lot of the stuff in the data mining also has to do with the infrastructure, right? Very large databases, being able to do parallel distributed computing, the whole cloud infrastructure and the big data infrastructure. I mean, all of those things are, offshoots, right, of this particular field, okay? Now, the other thing that is different between, let's say, data mining and statistics is really the mindset, okay? So data miners believe that all the information is in the data, right, and let the data generate, both a hypothesis as well as test those hypotheses, right? Which is a little bit different from a statistical point of view, in which someone that does a kind of trained to be a statistician, starts with a hypothesis, right, goes and collects data, right, and then tests that hypothesis. Okay, so data miners, they figure out, well, we will generate all the possible hypotheses that the data support, and we're going to use the data to actually test those hypotheses, right? And so this is really kind of the whole idea of data-driven versus, hypothesis-driven. By the way, if you guys have any questions, feel free to interrupt. Okay, so people in data mining, they're actually trying to solve two problems to a large extent, right? So the first problem is usually tends to be referred to as a prediction task, right? So what we're trying to do is we're trying to predict something that we do not know, okay? And the other one is a descriptive task. What we're trying to do is to describe something that exists in the data, okay? So for many of you guys who have taken a traditional AI course, right, not the deep convolution neural network AI, right? That becomes essentially the first part is usually tend to be called the supervised learning, right? And the second part is usually tend to be called unsupervised learning. You guys have heard those terms before? Yes? Good. Okay. So those are really the two classes of problems that people in data mining, right, that they're really trying to solve. It's building those predictive models, right? So use some of the variables that exist in my data to predict some information, right, that I do not have, okay? And the way I tend to tackle those predictive tasks is by using some sort of a supervised learning. So I have some data that's already labeled, and we'll get to that. And descriptive part is to really find some sort of a human interpretable patterns that describe the data. Okay, things like clustering is, for example, an example of a descriptive task. Okay, so and in trying to do those two things, right? We have developed gazillions of methods to do it, right? And the reason for that is those methods have different characteristics. They're designed to apply on different types of data, and so forth, right? So some of the methods like clustering we mentioned about. Building, let's say, a decision tree to do some sort of classification, methods to, for instance, to find anomalies in my data or outliers, things like finding association rules and I don't want to use the term causality patterns, but essentially patterns that will help me predict certain things. Okay, so just quickly go through that, right? So predictive modeling or classification, right? So the idea is, and I'm sure you guys have seen those things, something similar like that before. So usually what I have some sort of a data set, right, in which I have different records. Every record is described by a bunch of attributes or variables or features, whatever you guys want to call them, right? And one of those features is a special type of feature. We tend to call it like a class label, right? And our goal is trying to do is to try to build a model, like some sort of an algorithm, okay, that will predict that from that, right, using some data for which we already have the class labels, right? So the idea there is if another record comes down the road in which does not have that class label, then we can predict the class label with some level of accuracy, right? And here is a decision tree kind of a model that will do something like that. And we'll talk a little bit more about decision trees when we move forward. Okay. So examples, predicting tumor cells as benign versus malignant, classifying credit card transactions as being legit or fraudulent, right? Classifying secondary structure of protein to an alpha helix, beta sheets, or coils. Categorizing the different news stories based on, let's say, what they're talking about. Finding, intruders in the cyberspace and so forth. Okay. So clustering is another one of is now a descriptive task, right? The idea is we have a bunch of objects, those are described by certain features, and what we're trying to do is we're trying to segment or group those objects, right, into subsets, right, such that each subset is to some extent or along certain dimensions, more similar internally than externally. Okay, so like maximize some sort of a similarity property of a subset, right? So if my points in the three-dimensional space, you can guys see that, so this is like a cluster, this is a cluster, this is a cluster, okay? And the reason that I want to do that kind of segmentation over there is because, one use case scenario for that is if I have, I don't know, 1 billion records, I may want to do that type of clustering so I can do some sort of information compression, right? So identify like some sort of prototypical behaviors by picking some example from those clusters. So, so again, the applications, being able to create, customer segments so I can, market them in a specific way, group related documents thematically so that I can speed up my browsing. It's extensive applications in biological domains. I would like to be able to group genes that they're similar because, a set of genes that they behave similar in terms of, when they're active and when they're not active, right, will indicate that they are controlled in the same way or they work together to achieve a certain function. So that will give me essentially the functional blocks that exist in our cells. Group stocks and similar price fluctuations so that if I want to have a diversified portfolio, make sure I don't get 10 stocks that they're semiconductors, right? All of them move in the same direction, right? So I will pick up something here, something from there, and so forth, right? And then, the other thing that you use clustering for is really to summarize, information compression. Okay, so you guys are quiet. And another example of those descriptive tasks is like association rule discovery. So this is like I would say the poster child of the examples for data mining people, right? So, you guys, I'm sure, have seen the beer and the diaper. The diaper and the milk implies beer example at some point in time in your life. Who hasn't seen something like that before?
Does experiencing count?
Does experience count?
Does experiencing living it?
Oh, experiencing it, I see. Sure, it does. So anyway, I'm sure you guys have heard a version of that story before that says that, I think, what it was Teradata when was trying to sell data mining technology to Walmart, right? So they say, well, we applied our cool data mining technology, and we found that, on Fridays, there's a Friday there, late on Fridays, right? People who go to the store, they seem to be, whenever they buy diaper and milk, they seem to be buying, beer as well, right? And great idea. And then they build a story behind it. So it's the fathers, you get the call from the wives, stop and get some milk and diapers, right? And then of course, it's late on Friday, so some beer for the weekend. That's the whole idea, right? Now, why the thing is important is because, someone knowing that, right, what it can potentially do, it can decide how to place stuff in the store, right? So you can put, diaper and milk and beer together. That makes sense to me, right? So anyway, this is kind of, the idea of those association rule discovery. Now, so that is a story about Teradata talking to Walmart, right? And I think it was 6 or 7 years ago, the guys who actually did that study, they confessed that this is an entirely made-up example. The example that came from analyzing, Walmart's data was nothing like that, right? But that was an easy example to put on a slide, so it got stuck. Okay, so
I have a question on that. Like, how would you determine that it's diaper and milk imply beer versus like milk and beer imply diaper, or like the milk to Coke, it's not Coke to milk?
That's very good. It's a great question. Just wait about 15 to 20 minutes, we'll get to that.
Great answer.
I know. Push it down. Okay, so anyway, so the association analysis, like a market basket analysis, rules are used for sales promotion, shelf management, inventory management, right? So, you can apply this type of analysis on data that comes in like a sequence of events data, to be able to somehow predict ahead of time whether or not something is going to fail by looking, for example, warning events in a log file, right? And a long time ago, we did a study like that, actually looking at the log files from routers, and then you can pretty much predict pretty accurately when they're going to fail, right? By the sequence of warnings that they start outputting prior to failing, right? And, and again, you know, in medical informatics, you know, you can use this type of analysis to identify, you know, what is the sequence of essentially medical conditions someone's going to start developing before, you know, getting something significantly more serious, right? So, and this is done by analyzing the data and finding those, you know, what's called, you know, association rules, which, by the way, it's nothing more than the condition probability of beer given everything else, right? So that's a quick answer to that. Okay? So, I mean, classification is not a new problem. You know, people have been trying to, you know, there's a lot of research, you know, goes, you know, more than, I would say, close to, definitely before my time, right, you know, in developing the classification algorithm, and the same thing for clustering, right? And I mean, association rule discovery is really something new that, you know, people in the data mining community introduce, right? But then the question becomes, you know, why do data miners care about that? And the thing that I mentioned before is the challenges that data mining researchers, you know, are trying to address is how to apply those methods, or how to develop this class of methods, right, that can scale to extremely large data sets, let's say scalability, you know, high dimensional data sets, you know, data sets that, you know, they're not described by 2 or 3 or 4 variables, but they're described by, you know, 100,000 variables, right? Heterogeneous and complex data, right? You know, what if my data is not just transactions, right? But they are, let's say, social networks, right? You know, how do I classify things in a social network, okay? And first of all, what is that thing, right? Is it an individual? Is it an interaction? Or what, right? There are issues about data ownership and distribution, right? I mean, when we talk about extremely large data sets, right, and you know, commercial data sets that span different, you know, owners, right? The assumption that I can download everything on my Excel and do something, you know, simply breaks, okay? And I'd like to be able to do the analysis in a distributed fashion, be able to do the analysis without necessarily having to exchange the data, you know, to prevent, you know, for privacy reasons. I mean, there's a lot of stuff that I have to be able to do in order to allow me to actually, you know, perform the type of analysis. And, you know, there's a lot of, you know, non-traditional analysis that I have to do. So, so anyway, I mean, those challenges, right? IBM was extremely good at, you know, creating the 4V diagram, right? So you guys have seen the, you know, the 4V, and I think now there are like 5 or 6 V diagrams, right? About things like, you know, the volume of the data, the variety of the data, you know, the velocity of the data, you know, veracity of the data, and so forth, right? I mean, so volume has to do with scale, right? Variety has to do with different forms of data, right? Veracity has to do with, you know, being able to actually do that stuff in dirty data and uncertain data. And, you know, the velocity has to do with being able to do extremely fast, right? And especially in streaming settings, right? For those who are not familiar with the streaming settings, this is a setting in which, you know, essentially data comes into you in chunks on a continuous stream. I think of like your tweet stream, right? And you like to be able to analyze the data, update your models, you know, predict on the fly, you know, as you go down there, right? And the challenge with the streaming data is that you cannot afford to say that, well, I keep on retaining all the data, right? Because the fact that it's a streaming data, you're going to run out of storage, you know, pretty quickly, right? So, so anyway, so this is, you know, what really people who work in data mining that, you know, it was then renamed to big data. And I guess right now it's called data science, right? You know, I don't think we can stick with the name, right? You know, this is some of the stuff that people, you know, are concerned about. Okay, so this is kind of, you know, my intro to data mining type of thing. So I have 3 sets of slides, right? Each of them has, the first one is short, it's about 30 slides. The other 2 is about 100 slides each. Okay, so. But they're quick slides to go through, okay? So the slides that I have is essentially talk about, you know, association rules and finding patterns. And this is something I would like to cover because, you know, this is something that probably you guys are not familiar with, right? And then I'm going to talk about classification, which is, you know, probably sexier than clustering or unsupervised learning, right? And then if you guys haven't thrown me out of here, right, then, you know, we'll cover some of the stuff on the clustering side. Sounds like a good plan? Yes, sir. Good. I like the feedback. And the reason I like pattern mining is it's so rich in algorithms. I'm showing my biases here. Okay, so association rules, right? So the beer and the diapers, right? So a given set of transactions, right? So first of all, we want to find rules of that type of form, right? Such that if the left-hand side is satisfied, then there is a high probability that the right-hand side will happen. Okay, so this is really what the notation here means, right? So the best way of thinking of that, if you go back to your probability stuff, is a conditional probability of seeing milk, given I have seen beer and bread, is high. Okay, so we're interesting to find rules like that. Okay, so so first of all, the implication sign or even the conditional probability sign really it has to do with frequency, right? And does not necessarily mean causality, right? Anytime you see something implies that, right? Don't think that that is the cause that created that. Okay, I mean, causality is a very hard thing to actually being able to tease out. Okay, this is mostly that just a conditional probability of milk given beer and bread is high. Okay, and if you guys remember for the conditional probability formula, if you look at the frequency of beer, bread, and milk, right, divided by the frequency of beer and milk, that gives you the conditional probability. Right? I mean, this is just frequencies. Just co-occurrences. Nothing about something is causing something else. Okay? Okay, so let's quickly give you some definitions to make sure that everything else I say makes sense, right? So item set, okay, is a collection of one or more items. Like for example, the milk, bread, diaper. That's an item set, right? And the length of the item set is 3. Okay, so the number of items in the item set is the length of the item set, right? So the support count, denoted by sigma, right, is the number of times that a particular item set, right, exists in a database of transactions that I have. Okay, and by transaction, what I mean is a set of things that someone has done somehow together. Right? So let's think in a commercial setting. So this is essentially your basket. You went to the grocery store, you bought a bunch of stuff. That is your basket. We call that thing a transaction. Okay? So the support S is essentially the normalized version of the count. Right? It's count divided by the size of the database. Okay? Not a big deal, right? And a frequent item set, right, is an item set that occurs at least a minimum support number of times. So there's some sort of a user-specified parameter. It's called min sup, right? And if that frequent item set, if that item set occurs at least that many times, we'll call it frequent. Okay, those are just definitions. And if you guys want the slides, I'll be more than happy to mail you the slides. So. Okay, so the association rule, right, is something like X implies Y, right? And it's nothing more than as I said before, is a conditional probability of Y given X. Okay, so if you look at that particular database, right? So I have milk and diaper implies beer. So I look, what is the support count of milk, diaper, and beer? What is the size of my database, right? So it's divided by 5. So that has a so the support, right? And then in order to compute the confidence, this is essentially the support of milk, diaper, and beer. This is the support of the milk and diaper, and I get 0.67. Okay? So, I mean, there's nothing complicated over here. We good? Okay? So the task, the association rule mining task is defined the following. We're given a set of transactions, so a transaction database T, right? Our goal is to find all the association rules that satisfy the following 2 constraints. Number 1, each of them has to occur at least min sup number of times. Okay? And the confidence of those rules will be greater than or equal to something of a user-specified confidence, minimum confidence. Right? So those algorithms take as simple those 2 parameters. Minimum frequency, minimum confidence. Okay? And output is all the rules that satisfy that. Okay? So going back to your question, right? Why is that thing happening? Right? Because I'm pretty sure the reason that thing was selected because it's the one that had the highest confidence. Maybe not, right? So you can see that has the same confidence, that has the same confidence, that has the same confidence, and so forth, right? But it may be the case in a more realistic database than that, right? You're going to find something that, that will satisfy the minimum confidence constraint, right? And another rule derived from the same set of items may not, right? So that's why you don't output it, okay? So I use the word constraint, right? So those 1 and 2, we tend to call them minimum support constraint, the minimum confidence constraint. So we want to find the stuff that satisfy both of those constraints, okay? So this is a beautiful problem because it's trivially to define, given essentially a set of sets, right? That's what each transaction is, right? 2 numbers, right? And you want to find everything that satisfies those 2 constraints. Okay? So one way of solving that, while you give the thing to your classes and you guys go solve it, is one simple way to do that is list all possible association rules, right? For each association rule, compute its confidence and its support, okay? And then prune the stuff that would not satisfy. You guys agree with that? This is called brute force, right? Okay? And of course, every time you hear the term brute force, there's a caveat associated with that, right? So, so D over here is the number of distinct items that my store sells. Okay? So I'm a Walmart and I sell a total of 10 distinct items. Okay, that's what D here is. Okay? So that number over here is the possible rules I can generate from those 10 distinct items. Okay? So long story short, the number of things I have to evaluate is exponential on the number of distinct items, right? And again, this is a power set on a set of items. You guys always easy to think of a power set as think of I have a binary number that has d bits, right? How many integers will that support, right? This is the total number of set that exists, right? Okay, and this is just the item sets, right? And then for each of those items, and then I can generate a bunch of different rules, right? And this is where that thing comes from. Okay, so anyway, so the space is huge, so you have to do something a little bit smarter if you want to actually solve that problem. So yeah, we went through it. Okay, first of all, by the way we solve that problem. So remember, we have 2 constraints: the minimum support and the minimum confidence. Okay. So what is the observation here is that given a particular item set, milk, diaper, and beer, right? Either that thing will be frequent or not, right? If it's not frequent, then no rule will satisfy both constraints, right? Because the first constraint will be violated, right? So the way we tend to solve the problem is first we're focusing on finding the frequent item sets, right? And then once we find the frequent item set, then we find the high confidence rules from there. Okay? So the second problem is actually not very complicated, so I'm not going to talk about it, how to find the high confidence rules given a frequent item set. Okay? If you guys want to know how to do it, send me an email. I'll send you, 3 slides on how to do that, right? Okay? So that's why we tend to decouple, right? So we find the frequent item sets, and then we do some sort of a rule generation from that. So this is a key figure that anybody who's working in this field of finding frequent patterns, very quickly becomes familiar with. Okay, so this is what is called the lattice of the possible patterns that I have. Okay, so this is a case in which the number of distinct items that my store sells is 5, right? A, B, C, D, and E, right? And this is a structured way, right, of representing all possible item sets out of those 5 items, right? So every circle over here, right, is one of the possible item sets, okay? And the lattice is organized in such a way so that the items of size 1 is the first level, right? Or the items of size 2 is on the second level, items of size 3 is on the third level, and so forth. Okay? And And the edges over here, what we represent, is given an item set like BCE, that thing is connected to the previous level, right, based on all size 2 subsets that it has. So the BCE is connected to BC, BE, and CE. So if I drew my diagram correctly, those edges will be there. You guys okay? You know how the light is coming about, right? So the nodes of that are all possible item sets, arranged in a level by level, okay? And the edges connect between 2 successive levels, right? And the longer level is connected to the previous level. I mean, the largest is connected to the previous level, right? For each one of the less size minus 1 subset that it contains. Okay? So this is just a nice way of visualizing, you know, all possible solutions. Okay? And we'll use that thing. I mean, that is really guiding a lot of the algorithmic and optimization that exists. You guys okay with that, how the thing is coming about? Okay? And by the way, this is a lattice for the item sets. You can generalize the whole notion of a lattice for other weird patterns as well. Things like sequences, graphs. I mean, you know, that has been generalized to death. Okay. So here is the most important observation on how to actually control the exponential search phase of that problem. Okay. Actually, let me explain the thing here. By the way, that's why I like the iPads. I can do that. Okay. So let's assume that first I analyze my data set and I compute the frequency of A, B, C, D, and E. Right? And given the minimum support that I have, let's say all of those size 1 item sets are frequent. Okay? Okay? So then I generate all possible size 2s, which is the entire second level of that lattice. Okay? And then I go to my database, right? And I compute the frequency of those size 2s. Okay? And let's assume that AD is not frequent. You guys hear that? What can I do with that piece of information? Which other ones will I exclude? So essentially anywhere in that lattice that I can, you know, any path that can go from AD to anything below that, right, that attaches, right, can be thrown out, right, does not need to be considered. You guys okay with that? Because if AD is not frequent, any extension that contains AD cannot simply be frequent. Okay? And this is really, I mean, this is called it has a fancy name. It's called the anti-monotone property of the support constraint. We love fancy names, right? Okay? And this is really the workhorse, right, that is used to prune the search space of all those algorithms. Okay? So formally, the way it's defined, you know, for any pair x and y, those are item sets, right? If x is a subset of y, right, then the support of x, which is the shorter one, it's a subset, right, can only be greater than or equal to the support of the longer one, right? So then if I find that that guy is not frequent, the short guy is not frequent, right, any superset of that, right, that contains the thing as subset can simply not be frequent. Okay? So everything can be pruned. Okay? And this is really the crux of the idea of how to how control the exponential complexity of the problem. Okay? So we went through that. So that's why I have a lot of slides, but you guys are smart. You know, you get the idea. Okay? So I'm going to introduce you like a couple algorithms, right, that rely on that idea to actually structure the rest of the computations, right? So the granddaddy or grandmommy, you know, depends on how you look at that, of the algorithm for solving that problem efficiently is something called a priori algorithm. Okay? So that a priori algorithm is an algorithm that explores the lattice level by level, okay, and consists of really 4 steps. Okay? But before telling you the steps, let me define two things. So I'm going to define fk and lk, right? So, and also I need to show off that I can write calligraphic letters, using PowerPoint, okay? So, which nowadays you can, right? So you don't have to do LaTeX. F sub k, right, are the frequent k item sets. Those are the item sets of size k that they are frequent. So I have a database, right? And F sub k are the frequent size k item sets. That's good? Okay? And lambda k, or lk, right? I should not be revealing my nationality. Lk, right, is a set of items of size k that may or may not be frequent. I don't know. Those are called candidate size k frequent item sets. Yes, okay? So F are known frequent. L are size k whose frequency has not yet been determined. So they can be frequent. Okay? So then the algorithm works as follows, right? So it's an iterative algorithm, goes for k equal 1 through until I'm done. Okay? So first of all, generates the frequent item set of size 1. Okay? And then it goes into the loop over here, right? So it generates candidates of size k plus 1, essentially 1 longer, right? From the frequency of size k, right? Then it prunes candidates of size k plus 1 by relying on the anti-monotone property. So something that is generated of k plus 1, in order for the thing to have a fighting chance to be frequent, each of its size k subsets has to be frequent. Okay? So a k plus 1 has k plus 1 size k subsets. That's always funny if we go k plus 1 has k plus 1 size k. You guys agree with that? Take one out, right? So the k plus 1 to take out. So you essentially check each one of them to see if it's frequent. If at least one of them is not frequent, that the thing can never be frequent, so you throw it away. Okay? So they have essentially a pruned version of candidate that is like as tight as you can get it. Okay? And then you go to the database and you actually compute the frequency of each one of them. Right? This is where the work is spent in determining the frequency. Right? And then stuff that they're not frequent, you throw them away. Right? And that leads to fk plus 1, the frequency of size k plus 1. Right? Now, if that thing ends up being empty, you're done. Okay, if the thing is not empty, you go back to the top, right? And you proceed. You guys, you okay why the thing is a termination criteria? So if I have nothing of size 5, then we'll definitely have nothing of size 6, 7, 8, and 9. Okay? Because that size 7 has to have all of its subsets to be frequent, right? That means all the size 6 subsets have to be frequent. But if I have none size 6, then there's nothing to do. Okay? So this is really the algorithm, right? That part over here is computationally expensive, right? And that part over here is not if you do it in a smart way. That one will still remain computationally expensive even if you do it in a smart way, right? I mean, that's, that takes time because that actually has to go to the database, right, and compute the frequency, okay? Now, that part over here is essentially you want to generate the candidates, okay? And there is there's a cute way of doing it, when it comes to algorithms. There's a cute way of doing it, right? So what is called the fk-1 times fk-1, joint method. So remember what we're trying to do. We tried to generate, okay, I should not have called it k-1, I should have called it k. That's okay, but you guys can get it, okay? So for this slide, we don't want to get the lk plus 1, but we want to get the lk from the fk minus 1. We okay? So we generate size in k from the k minus 1, okay? So the way I do it, I take two k minus 1s, right, that have a common k minus 2, right, and put all those together to create a k plus 1, a size k. They steal all the markers from here. Oh no, it isn't marker here. Okay, I want to go to k, right? So I have 2k minus 1s, right? That have the same k minus 2, right? To give me that. So that thing contains the common k minus 2 plus 1 over here that is different plus 1 over here that is different to give me a size k. You guys agree with that? So in that way, it's a very tight way of doing candidates called candidate generation. Okay? And then you rely on some other interesting tricks. Your frequent guys, you sort them in lexicographical order within each item set, and then you sort them those guys, right? And the way you do the joint is essentially you merge. So if I have, for AB, right, for AB over here, I merge it with the stuff prior to me that have the same, k minus 2 prefix, right? That thing over here, I have to merge with everything prior to me that have the same k minus 2 prefix, which is none, right? The same thing here, none. The same thing over here, none. So it's a very efficient algorithm. You just, it's like a double for loop. From I, you go to the one preceding to that, right? And see whether or not they have the same k minus 2 prefix. Okay? So that's one part. And then if I want to do support counting, this is where a lot of the interesting part about that algorithm comes in, is remember I have those candidates that I want to determine their frequency. So you tend to create some sort of a tree structure like that, in which you group the candidates, right, into buckets, such that the k minus 1 prefix is the same. Right, so those are the candidate item sets. Okay, and I have them in some sort of a tree-like structure like that. Okay, so each of those buckets, right, contain the stuff that the k minus 1 prefix are the same. Okay, and then what you do is you pull out a database transaction from your database, right, and you traverse that structure in some sort of a nice way, right? So you pick up the one item. You go down here, and then you pick up the 1, 2, the second part, you go down here, and then inside here, you check to see if the 3, 5, 6 occur. And if they occur, then you increase the frequency. If they do not occur, then there's no corresponding size 3 item sets. So anyway, it's a tree kind of a structure that allows to do computation efficiently. So instead of taking an item set, comparing against the transaction, what you do, you take a transaction, and you compare against all the item sets. Make sense? I mean, that's kind of the idea of that data structure. This is not a 1-minute visual, but the key takeaway here is there's a lot of interesting, weird data structures to allow you to do that thing efficiently. And get even significantly more weird. But this is kind of interesting part, right? So this is a so I have those two parameters in the algorithm. It has to do with both the confidence and the support. And this is just a study of the support. So this is what happens to the number of candidate item sets, right, as a function of the size of the item sets for different values of support. Okay? So if my support is pretty high, like 0.5%, right, there are not that many candidate item sets, right, that the algorithm will terminate right away, right? If I decrease my support to 0.2, right, then I'm in that line over here. I have some more guys over here, right? If I go to 0.1, then the number, gets significantly higher, right? If that thing gets further reduced, that would go even higher, okay? So, I mean, what the chart shows over here is that the complexity of the problem, right, number one is a function of the output set, how many results are valid, right? And the number of valid results is a function of my support. So if I look at something that are highly infrequent, expect a lot of results and expect a huge amount of time, okay? If I'm looking at stuff that they are not, that, they have, high frequency, the whole thing will run very fast. Okay.
So can you go back?
Yes.
Sorry about that. But what's the intuition of the odd shape of the...
So the intuition of the odd shape of that thing is what is happening over here. It's the same thing as the lattice over here. Where's my lattice picture? Okay, so look at the lattice picture. This, of course, is a very trivial example, right? But you start with a relatively not very wide level on the tree, on the lattice, right? And then that thing expands and then shrinks, right? 1, 5, and the more items the thing expands. So what is happening is that, you get the idea? Good. Do you guys get the idea? Because,
I'm just pretending over here. No, it makes sense.
Yeah, so essentially,
and then it shrinks down.
yeah. So that is what is happening. And the reason for that is because, for a certain size, the possibilities become extremely large, right? And then as the size increases, then they have fewer choices at that point in time.
Because the item sets of 1, you can only have as many of those as you have items.
Yeah.
Right? But of 2, you all of a sudden... Right.
So anyway, the other part over here that is really the takeaway message, another takeaway message over here is the number of item sets that come out from those algorithms can be extremely large, okay? And there has been a lot of research focused on potentially reducing the number of item sets that I find without necessarily, right, reducing the value of from the association rules. You guys understand? So instead of finding all frequent item sets, right, can we somehow find a smaller subset of those item sets and still have the ability to generate high confidence association rules? Okay? So, so that's why people introduce the whole notion of maximal and closed. So a maximal item set, right, is an item set that a maximal frequent item set is an item set that all of its extensions are infrequent. You guys agree with that? So size 1 can be potentially extended to size 2 that is frequent. That size 2 can potentially be extended to size 3 that is frequent. That size 3 may, if I try to extend it to size 4, all of those size 4 are infrequent, right? So that size 3 is maximal, right? So in that particular picture, right? So for instance, AE is frequent, but its extension is also frequent. So that thing is not maximal, right? But that guy over here, right? Any of its extensions over here, are infrequent. This is called the border of frequent versus infrequent. Everything underneath is infrequent, everything above is frequent, right? So this is a maximal, this is a maximal, this is a maximal, right? So one way that people have explored to try to reduce the number of item sets that they find is to focus only on maximal frequent item sets, okay? That actually turned out not to be a good idea. So they focus on something else. It's called the closed. Okay.
So how many papers were published before they decided that was...
Quite a few. Okay. Quite a few. So, and then they hit to the whole notion of a closed frequent item set, okay? So an item set X is closed, right? If all of its immediate supersets, okay, have a lower support than X. You guys hear that? So I have a particular item set, right? And all of its +1 extensions have a support that is lower than X. Okay? If that thing happens, it's called closed. Otherwise, it's not closed. It's a beautiful definition, right? So if extending that item set, right, if all of the extensions of that item set have a lower frequency, right, then it's called closed. If at least one of the extensions has exactly the same frequency, it's not closed, right? And again, by frequency over here, this is nothing more being supported by the same set of transactions. So that's really what a frequency over here is, right? So, and there is a very complicated example which, that will not give me time to go through it, but this is a relation that exists in the big Venn diagram relation, right? So the big circle is the frequent item sets, right? The somewhat smaller circle are the closed frequent item sets, and somewhere over here, the maximal frequent item sets, right? And that nested property exists, okay? But you can show if I have the frequency of the closed frequent item sets, right? I can precisely determine the frequency of something here, You guys understand the statement? If I know the frequency of those guys, the guys inside the closed frequent item sets, okay, then I can, given an item set over here that is not closed and frequent, but is not closed, right? Then I can determine its frequency. Right? Remember what is a not closed frequent item set. An item set is not closed if at least one of its extension has exactly the same support as that set. You guys agree with that? So there's at least one extension of that that has exactly the same support. Okay? Now, if that extension is closed, then I know its support. If that thing is not closed, it means an extension of that will have the same support. Keep on doing it, right? So I can run my frequent pattern lattice in the reverse direction. It can determine the frequency of the stuff that they're not closed. Okay? And the beauty is I can develop efficient algorithms to find just those guys. And from that information, I can determine that with no ops. No operations, right? So fast. Okay? And that part over here, I can do it very efficiently.
How much smaller is the closed frequent?
Can be, at least in many cases, it can be as large as the frequent item sets. It can be significantly smaller. So the visual of the closed things is the following. So, so this is my transaction database in a matrix format. Okay? So if I have a bunch of transactions, right, that have each column is an item, right? So this is like an item. Each column over here is an item. If I have a sparsity structure like that in my data set, right, then the only thing that is closed here is the 5 size item sets. Okay? And any subset of that is not closed, because there's at least one extension of it that has exactly the same support. Okay? So that will lead to an exponential reduction in the number of item sets that are actually identified. You guys get the visual here? So first of all, is my picture, each row over here is some sort of a transaction, right? And the ones over here correspond, indicating that that particular transaction has that particular item. Okay? So if I view my transaction database as like a matrix with the items that they are present as ones and everything else as a 0, right? And let's say those are the ones from those 4 transactions. Okay? And let's assume for now that none, the rest of those items do not occur in anything else, anywhere else, right? So this item by themselves, let's say, is their frequent, but they're not closed, right? Because I can take that item, extend it by adding the other one that has exactly the same support, right? Even that size 2 is not closed, because I can extend by adding another one, it will have exactly the same support. The size 3 is not closed, because I can extend it by adding another one from here, will have exactly the same support, right? The only one that does not have the same support is the one that contains everything. And that is the one that gets discovered in the closed and nothing else, prior to that, right? So in this particular case, instead of finding, 2 to the 5 possibilities, it only finds 1. Okay, so that's where the dramatic reduction in those cases comes in. Of course, it's data set dependent, but if you think about a grocery store kind of things in which people tend to buy stuff in sets, like they're driven by, recipes and things like that, right? I mean, that tends to lead to a dramatic reduction in the number of item sets. Okay, so I need to spend a few minutes here because this is beautiful. You guys can appreciate that. Okay, so we talked about the pattern lattice, right? And we say we're going to expand it level by level, right? But I can also do it in a depth-first fashion. You guys agree with that? So I can explore my lattice in a depth-first fashion. I can find A, then extend, get AB, then ABC, then ABCD. They can backtrack over here, find ABD, and so forth. Right? So they do a DFS of my pattern lattice. Okay, so so this is, for instance, here's my lattice, and here is how the lattice will be explored if I'm going to do a DFS on it. Okay, so one of the drawbacks of the level by level way of doing it, in order to generate that, I need to have the frequency of those guys. In order to generate that, I need to have the frequency of those guys. If the thing becomes extremely wide, it can easily be the case in which the amount of memory required to store those guys will be comparable to the size of my database. Okay, and we'll definitely not have enough memory to store it in memory. My database usually they seem to be on the disk, right? That thing can become extremely wide, right? So the memory of that thing can just blow up. Okay, so the simplest way to control the memory blow up, instead of exploring the thing in a breadth first, level by level, you do it in a DFS. Okay, so and there's a whole set of methods I have been developing to do the DFS exploration, and the beauty about those methods is that, and I'm just describing you high level, and I'll give you the gory details, is as I go here, right, so the idea is the following. I find all the transactions that contain A, right? And then in that set of transactions, right, I find all the transactions that contain B, right? And in that set of transactions, I find all the transactions that contain C. And in that set of transactions, I find all the transactions that contain D. So if you guys followed what I said, as I go down here, and assuming the frequency of those guys progressively decreases, right? Because the frequency will only decrease, right? Never increases. Okay? Then the size of the database in which I do that discovery becomes progressively smaller and smaller and smaller. Okay? So as I go down, right, number one, I operate on progressively smaller and smaller and smaller databases to the point that I can make those databases to be in memory. Right? I can store them in memory. So that leads to huge efficiencies of that. And in terms of the memory requirement of that, it's proportional to the path. Right? I mean, that's the whole idea of DFS versus BFS. Right? And when you do a BFS exploration, you need to store the previous frontier. Okay? In a DFS, you just need to store the path. Right? But as you go down here, what you do, you also save in the database. And that leads to very efficient algorithms. And those are called projection methods, by the way. And tend to lead to algorithms that they're recursive, like a 3-line algorithm. Right? So this is like TP stands for tree projection. Right? So it's just like the way you do a recursive exploration in a depth first, right? The same idea of those algorithms, right? And this class of algorithms is the current state of the art of actually mining those frequent item sets. Okay? So beyond transactions, so the idea that I talked about, the level by level exploration, the depth first exploration, has been generalized to beyond item sets. The two most widely used type of data that people apply those things besides transactions are sequential data sets. This is like a sequence of transactions, if you want to think about it. Sequence of web page visited, the sequence of articles read, biological sequences in the DNA or amino acid sequences, event logs and so forth, right? So people trying to find association rules in those kind of, temporal data, sequential data. And then the other area in which has been a lot of work is really finding association rules in relational or graph data sets, like social networks. People do analyze to find association rules there. Chemical compounds. The most robust way to represent a small chemical compound for drug discovery purposes is to represent it via its molecular graph. Right? Every atom becomes a vertex, right? A bond becomes an edge. Okay, and then do that frequent pattern mining in those graphs, which become really a frequent subgraph discovery, and you can use the things to build association rules to do things like drug discovery, web pages, information networks, and so forth, right? So anyway, there are tons of papers, books, whatever have been devoted in actually generalizing those things in those different types of data types. other than just a set of transactions. Okay?
Quick, some questions, just to get me a sense of scale. You say, on a couple of slides back, you don't need to go back, but you were saying you can keep a lot of stuff in main memory rather than go to disk.
Yep.
In your world, what's main memory? I mean, how much memory is that?
Well, if you do data processing on a serial machine, right, the memory usually that people assume you have access to, like, it's not, I don't know, 32 or 64, 128 gigs. I mean, all of those methods are designed to operate, assume that the database is on the disk. You guys agree with that? So the database in general is assumed to be so big that it cannot be brought in memory, right? So the memory is used, primarily, right, to store in a priori kind of algorithm, to store the candidates and the frequent item sets, because you do need those guys when you do association, rule generation. Okay, the part that I did not talk about, right? But the database assumed to be on the disk. On the projection type of stuff, after a couple levels of projection, the database on which you operate is fairly small, right? So you can actually load it in memory, okay? But in memory, usually, it's not uncommon to assume I mean, those algorithms can run on laptops with 16 or 32 gigs. I mean, they're pretty flexible in terms of memory footprint. Any other questions?